This was not a pilot error. It was not a mechanical failure. It was a single sensor, no bigger than your fist, that hijacked a jet and flipped it on takeoff. On October 29, 2018, Lion Air Flight 610 lifted off from Jakarta, and within minutes, the aircraft rolled hard over, diving into the Java Sea. No pilot input, no warning, just a silent, deadly command from a computer that trusted the wrong data. This is wings and wrecks, how machines fail and what saves the people inside them. How could a sensor smaller than your hand defeat 2 trained pilots and a multi-billion-dollar machine? The angle of attack vane, a tiny fin on the fuselage, measures how the wing meets the air. When it fails, it feeds a lie to the flight computers. Those computers, designed to protect the aircraft, act on that lie even if it means rolling the plane into the sea. Why did a sensor smaller than your fist hold such power? The angle of attack vane, a slender fin barely a foot long, measures the angle between the wing and the oncoming air, a number the flight computers trust absolutely. That number is not a suggestion. It feeds directly into the flight control laws, the software that decides how the aircraft responds. In fly-by-wire jets, these laws can override the pilot's own inputs, prioritizing the computer's judgment over a human's instinct. And that is the trap. When the vane fails, it feeds a lie, and the computer, designed to protect the aircraft, acts on that lie. The pilot's fight is not against the machine, but against its trust in the wrong data. How does a lie spread through an aircraft? In 2009, Air France Flight 447 fell into the Atlantic when ice clogged its pitot tubes, feeding the computers a stream of impossible speeds. The autopilot gave up, and the pilots, left with a jet that no longer made sense, pulled the nose up until the wings stalled. The sensors had lied, and the crew paid the price. But here's the catch. In AF 447, the sensors failed, and the computers disconnected. The pilots were left alone. In the 737 MAX, the computers did the opposite. They trusted the lie and they acted on it, pushing the nose down with a force the pilots could not override. The sensor's failure became the aircraft's command. And that is the question that haunts every accident investigator. How do you design a system that can tell the difference between a lie and a truth? The answer, it turns out, is harder than anyone imagined. Why did a safety feature become a death trap? MCAS, or Maneuvering Characteristics Augmentation System, was a software patch designed to make the 737 MAX handle like its predecessors. But MCAS trusted a single angle of attack vane, and it had the power to push the nose down again and again, no matter what the pilots did. MCAS was a workaround, a way to make a fundamentally different engine placement feel like the old 737. To do that, it needed to act fast and hold authority. Boeing gave it the power to trim the stabilizer nose down, based on just one sensor's data, even when the pilot pulled back on the yoke. In the cockpit, the crew had no idea this system existed. They'd been trained on the old 737, where a runaway trim was a manual problem. But MCAS was invisible. No warning light, no checklist. And when it fired, it didn't just fight the pilots, it overrode them, pushing the nose down with a force they couldn't match. On the morning of October 29, 2018, Lion Air Flight 610 lifted off from Jakarta, bound for the island of Bangka. Minutes into the climb, the nose began to pitch down on its own. The captain fought the controls, pulling back with all his strength, but the system pushed again and again. This was not the first time the aircraft had misbehaved. On the previous flight, the same sensor had failed, feeding the computers a false reading. The crew had wrestled the jet to the ground, and the logbook noted the problem. Yet the plane flew again, with the same faulty vane still installed. A single fist-sized vane, already known to be lying, was trusted by the computer to command the stabilizer. The crew had no training for MCAS, no warning light, no checklist. They were fighting an invisible enemy that kept pushing the nose down, until the sea rose up to meet them. So why didn't the redundancy save them? The answer is a paradox. Multiple sensors only help if the system can tell which one is lying. If it can't, the error doesn't cancel out. It spreads like a rumour through a crowd, gaining authority with every node that repeats it. In the 737 MAX, MCAS trusted a single vane. When that vane lied, the system had no way to know, so it acted, forcing the nose down again and again. Redundancy only saves you when the system knows it's wrong. Here it didn't. That's what turned a sensor into a killer. What does a repeat of the same failure look like? On the morning of March 10th, 2019, Ethiopian Airlines Flight 302 lifted off from Addis Ababa. Minutes later, the crew radioed a mayday, flight control problems. The same impossible fight had begun again. But this time the roll came faster. The crew never got the chance to fight back. 6 minutes after takeoff, the jet plunged into the ground, killing all 157 people on board. Investigators found the same signature, a single faulty vane, feeding MCAS a lie. 2 crashes, 5 months apart, same sensor, same software. This was no one-off, it was a pattern. Why didn't anyone stop it? In March 2019, the FAA grounded the entire 737 MAX fleet, a move that would last 20 months. Boeing's fix was simple in principle. MCAS would now require both sensors to agree before it could act, and its authority was sharply limited. The deeper lesson wasn't about software, it was about trust. Redundancy only saves you when the system knows it's wrong. The fix ensured that a single vane could never again hijack a jet, but it took 2 crashes and 346 lives to teach the industry that. The lie doesn't stop at MCAS. That false reading ripples through the entire flight control network, the autopilot, the trim system, the stall protection, each one accepting the same bad number. It's like a rumour that gains power every time it's repeated. Because the computers are designed to cross-check, not to question, the error becomes the new reality. The pilots aren't just fighting one system, they're fighting a cascade of commands, all born from a single faulty fin. In Air France 447, the autopilot simply disconnected, leaving the crew to fly a jet with inconsistent airspeed readings. The pilots, trained to trust their instruments, were suddenly on their own. They pulled the nose up, the stall warning blared, and the aircraft fell. The lesson was harsh. When automation abandons you, the human must be ready to take over, but only if they understand what the machine was doing. In the 737 MAX, the computers didn't disconnect. They doubled down. That's why the fix was so crucial. MCAS now requires both sensors to agree before it can act. A simple change, but it means a single faulty vane can no longer trigger the system. The cost was 346 lives, and the lesson is stark. When you build a system that trusts one sensor, you're building a system that can be hijacked by one failure. The lesson extends beyond Boeing. Every fly-by-wire aircraft, every automated system, faces the same challenge. How do you know when your sensors are lying? The answer isn't more sensors, it's better logic. Systems must be able to detect disagreement, isolate the faulty component, and fall back to a safe state. The 737 MAX taught the industry that automation isn't infallible. It's only as trustworthy as the data it receives. The plane that flipped on takeoff was never the plane's fault. It was the lie it believed. The fix came with a simple rule. 2 sensors must agree. But the lesson is harder to fix. Redundancy only saves you when the system knows it's wrong. That's the mechanism under stress, the one we'll keep dissecting, one sensor at a time. If you want to know why machines break and how crews fight back, subscribe. Next up, our next video.